How y'all doing?
Good.
Happy November. Any questions before we get started? All right. So, last time we started chapter 8 and started talking about additional rotational concepts and how they tie back to their old-fashioned linear counterparts. Basically, anything we've discussed that has to do with linear motion has some sort of rotational counterpart. We began this week's discussion with torque. We're going to continue that today, at least to start with. As a reminder, torque, as the angular counterpart to force, behaves very similarly to it. If all of the forces acting on something add up to zero, the object is in equilibrium and it shouldn't accelerate. Likewise, if all the torques acting on something add up to zero, the object is in rotational equilibrium and will not angularly accelerate. The question we looked at involving this last time was a teeter-totter. The two kids on either side of it have to exert equal and opposite torques to keep the object physically in place. We're going to look at another couple examples involving that today. We're going to switch it up slightly though. In this scenario, we had two forces on two different sides of a pivot point. Now we're going to look at multiple forces acting on the same side of a pivot point. This is, I'm envisioning it kind of like an old-fashioned shop sign, the kind that you might see hanging above a store's door as you're walking through like small town, downtown, that sort of thing. And what we've got here is a metal pole that is physically bolted to the building by a hinge on one side, so it can rotate about that hinge. So this is now our axis of rotation, not the middle like with the teeter-totter. And there are two things physically tied to this particular object. First is the big old cast iron sign that is hanging from one end of it. Mass of 100 kilograms, and it is exerting a force right here at the very end of the flagpole. The pole's 1 meter long, so that force is being applied 1 meter away from the axle, from the hinge where it's attached to the building. Now, if that sign was the only thing attached to this flagpole, what would the pole do? It'd fall. More specifically, that weight would exert a force on the pole at this radius from the hinge that would make it start spinning clockwise from our current perspective. And if this physical object starts rotating clockwise, it's just going to fall until it clings against the building, and that sign might swing down and break someone's head, which would be bad. We want to avoid that. To avoid that, we have to note again, this is generating clockwise torque. We have to cancel out that clockwise torque with some counter-clockwise torque. And that is where this rope comes into things. This rope is physically tied to the flagpole, and its job is to generate counterclockwise torque to mitigate the clockwise torque of the signpost. That rope is tied 0.3 meters. One sec. Hello. That rope is tied 0.3 meters from the hinge. So this force is going to generate torque here. And note that if you exert a force upward right here, given where the hinge is, that would create counterclockwise torque. So this rope, the job of this rope is to keep the sign in place, keep it from swinging down and hitting the building. And so we need to balance those torques. Does the basic setup feel all right where we're starting from? All right. One thing I want to illustrate here is that sometimes forces acting on the same side of a hinge but in different directions can create opposite torques. Likewise, two forces pointing in the same direction on opposite sides of a fulcrum, like with a teeter-totter, still generate opposite direction torques. So, we need to get all of our torques here to add up to 0. Because if the object isn't accelerating, net torque is 0, like how we want net force to be 0 to prevent linear acceleration. So, net torque needs to be 0. So we have to take all the torques acting on this thing, add them up to 0, and figure out how much force is required in that rope to make sure that's what's happening. This is very similar to what architects do all day. This is the branch of physics we call statics. The goal being, make sure everything stays in place so it doesn't fall and break. So, we need to identify every single torque present here and add them all up to 0. So, first off, let's start with the torque we're kind of after here, the torque being generated by the rope. There is also going to be torque generated by the sine. Well, bless you. Those are two different forces that are going to be acting at two different radii. And so they will both generate torque, and the torque in the rope has to be enough to mitigate the torque in the sine. So very similar to the teeter-totter case from the other day. We've got two torques that have to cancel out. Weird thing is that they're both, the forces in question are both on the same side of the hinge. But there's a there's another weird thing. There's another weird thing we need to consider. Say that rope wasn't there, but also say that the sine wasn't there. We just have the flagpole on a hinge on the building. Again, it's able to rotate about this hinge. And if it was completely alone, no sine, no rope, what would this thing naturally do by itself? If it's just a piece of metal bolted to a hinge? Fall. Physically take any stick, allow it to rotate about one end, and then don't support it, it falls. Why? There's no sine hanging from it. Gravity of itself. The weight of the pole itself does actually matter. And that is because the center of mass of the flagpole is not being supported. If you'll recall, if you've done lab this week and also in the example for Monday, we were looking at a seesaw. And this piece of lumber has a mass, so it has gravity, and that gravity can generate torque. But seesaws tend to put the fulcrum right under the center of the object, right under the object's center of mass. So, some new information. Center of mass is a physics concept that says that an object's entire mass can be treated as if it's a point mass at one spot. And for uniform objects made out of a single material and of a standard geometric shape, that spot is usually dead center. In the case of, say, a stick, or the physical body of a teeter-totter, this object's center of mass is its middle. This is a 2 meter long meter stick, so dead middle of it would be 1 meter from either side. And I can treat this object as if it is a single point mass right there in the middle. And as long as that means that the force of gravity on the stick is acting right here in its center. Now for a teeter-totter, that's usually where you put the fulcrum. And that supports the weight of the object. So it's not falling right now. Right now, if the meter stick is considered a point mass at its center of mass, then that entire mass is basically right on top of my finger right now. It's as if the rest of the stick may not exist. The entire stick is just a dot on my fingertip. As long as I'm supporting that one spot, the entire stick is fine. Whole stick moves with my finger. If I am not supporting that spot, I am no longer supporting the entire object. And now that force of gravity is located a distance away from the fulcrum being my finger. And when force is exerted away from a fulcrum, you get torque. So for teeter-totters, as long as the fulcrum is under the center of mass, the mass of the object doesn't really matter. You could make it out of osmium if you wanted to, and its own weight wouldn't affect the torque. Osmium is the most dense thing that I know of. But if that center of mass isn't supported by the fulcrum, then its mass matters. Then its matter matters. And in the case we were just looking at, the center of mass of the flagpole is not being supported by the fulcrum, because the fulcrum is bolted on one of its ends, is not under its center. Again, if this was just a pole with a hinge on the side, it would fall. And that's because its own weight, acting directly center of the object, is now a radius away from the hinge. That torque generates angular acceleration if it's not counteracted, and so that's why the pole by itself does still swing down. So there is a third torque here. There's the rope generating counterclockwise, there's the weight of the sign generating clockwise, but there is also the weight of the flagpole itself acting right there, halfway down the length of the object, that is also going to generate torque. And the rope has to cancel out that too. So there's three torques we have to consider. Note this big old gap I left in my formula over here. Three torques must add up to 0 in this case. 2 of them are clockwise, 1 of them is counterclockwise. How does this feel so far? Center of mass is one of the new things we're talking about today. So that's a new concept we're exploring here. We're also exploring that multiple torques, more than 2, can add up to 0 sometimes, like how loads of multiple forces can all add up to 0. So 3 torques we need to balance here. Torque is equal to force times radius, so we're just going to pop this formula in for each of those single torques. We've got radius rope times force rope plus radius sine times force sine and radius pole times force pole. And all these torques must add up to 0 to keep the sign from spinning. 3 torques, factoring in all 3 of them. Good so far? All right. Now force rope is what we're after. We want to know the force the rope has to exert to hold this thing up. Because if you were building this, you basically need this information to figure out what kind of rope to use. It's probably going to be a really big force. You need to know what tension the rope has to be able to withstand so that it doesn't snap. However, that is a very heavy sign, so instead of rope, it's probably going to have to be like braided metal wire. Now, we don't know force rope. That's what we're after. But we do know where that force is applied. is the rope is physically tied 30 centimeters away from the hinge. So that force is applied at a radius of 0.3 meters. So we don't know the force, but we at least know where it is acting. We also know where these other two forces are acting. The sign is hung 1 meter away from the hinge, so that's its radius. The sign also weighs 100 kilograms times negative 9.8 newtons. So its own weight is the force it is contributing. As for the flagpole itself, its weight is acting halfway down its body at its own center of mass. So if it's 1 meter long, that center should be halfway down its length. So 1 divided by 2 is 0.5. And then the force it is going to contribute is its own weight, 5 times negative 9.8. Once again, all of these must add up to 0. Concerns, questions? Wordless, vague, frustrated expressions? All right. F rope is the only thing left to solve for. So, torque from the sign, 1 times 100 times negative 9.8 is negative 980 Newton meters. Torque from the flagpole is 0.5 times 5 times negative 9.8, which is 24 and a half? Negative 24 and a half. So to get F rope, we're going to need to send the negative numbers over to the other side, divide both sides by 0.3. So F rope equals positive 980 plus positive 24.5 over 0.3. And that is going to end up being, please let me know if your math disagrees. A required force of 3,350 newtons, which is a lot. The sign's too dang heavy. I kind of made the sign purposefully large to show how silly this is. This is my mass. Massive and adult human. Yes?
Where's the 0.5?
Yes, so the flagpole itself is, where did I say that? 1 meter long. And that means that its center of mass is dead center of it, which is 0.5 meters from either side. So just one divided by 2. And if its center of mass is here, 0.5 meters away from the hinge, that is the spot where the sign's weight, where the pole's weight is going to act. So the numbers here, this is the distance that the pole's mass is from the hinge, and this is the weight of the pole, 5 kilograms times negative 9.8. Does that answer the question? Okay. This happens because the hinge is not under the object's center of mass. If it was, like with a seesaw, it wouldn't matter because the radius between these 2 points would be 0 and the weight of this doesn't factor in for that reason. But here the hinge isn't under that spot, so it does create torque.
Wouldn't force of gravity be Newton meters?
Torque is Newton meters, but here we solve for force, which is just newtons. We basically took 2 torques here, added them together, divided by meters, so Newton meters over meters is just newtons. How does this feel? couple of things to note if you ever do have to hang a sign like this. One, this is too dang heavy. I don't know why they have a lump of cast iron the mass of a human hanging from the end of this thing, but this thing should be smaller. Secondly, if you wanted to reduce that tension required in the rope, you could simply move the rope to the end of the pole. Because if it's a further distance away from the fulcrum, it's going to generate more torque. You need less force that way. So if you ever need to generate more torque, just apply your force further away from the fulcrum. Same is true for tools, really. If you ever need to use a crowbar, apply the force at the very end of the crowbar. Speaking of, you ever have to use a hammer, don't ever grab the hammer right under the hammerhead. Hold it at the very end of the handle. If you're holding it under the hammerhead, you're really just punching using the hammerhead. All right, questions about this one? All right. Now, we're learning a couple of new things today. One of them is about center of mass, so I want to put this back up and talk about it a brief second longer. We've talked about mass a lot this semester. You know, force acts on mass to cause it to accelerate. Mass affects how much an object wants to move. The more mass something has, the harder it is to make it move. But now that we're talking about rotation, there's a couple topics, more in-depth topics about mass we need to discuss. One of them is, again, center of mass. Alternatively titled center of gravity. They're just synonyms. I might switch between the two sometimes. They mean the same thing if I ever do switch between the terms. An object's center of mass can be considered, again, the one spot where the entire mass of the object rests. As long as you know where something's center of mass is, you can treat the entire object as if it was an infinitely small speck right there. Same as this applies to, meter sticks and flagpoles and teeter-totters and things like that, but it applies to everything as well. Remember last week when we were looking at gravity and how it acts as a centripetal force? And how the radius we needed to find the force of gravity between the Earth and the Moon was not the distance between their surfaces, but rather the distance between their centers. That's because the distance between their centers of mass is what affects their gravity. The center of mass of any object is also the center of its gravitational effect, because that's the one spot where functionally all of its mass rests. That's again why the center of the Earth counts for this calculation we did, not the edge of the Earth. So an object's center of mass can be kind of subtly important. For this class, it will mostly apply in terms of remembering this fact, that it's the center of the Earth's location that matters for its gravity, not the edge of the Earth. It'll also count occasionally in cases like this, namely just noting whether or not the center of mass of an object is supported or not. If it is supported, the object's mass shouldn't generate torque. Once again, you can do this with a meter stick. If the center of mass is supported, its own weight shouldn't generate torque. If the center of mass isn't supported, then its gravity will generate torque. Lab this week involves that, so if you haven't had lab this week, do bring notes from this to that. But it is useful advice if you're ever stacking boxes. You want to make sure that the center of the box is directly supported by whatever it's sitting on. My water bottle here can be hanging over the edge of the table as long as its center is directly supported by the table. If its center isn't supported, then it falls. It's also weirdly useful information if you ever need to kick something, Because if you kick something in its center of mass, it's as if you kicked the entire object all at once. Again, I did Taekwondo as a kid, so it's time to bring that back into things. Say I needed to kick that door open. Kicking the bottom of the door is not nearly as effective as kicking the center of the door if the goal is to make the door move. Kick the center of mass of the door, you kick the entire mass of the door, you can make the entire door accelerate. Same is also true of humans. If you ever find yourself needing to kick a human away from yourself, we aren't uniform shapes, so our center of mass is kind of harder to calculate, besides the fact that we're made out of a lot of different materials. So it's not always in the same spot, but it's usually somewhere in a person's torso. So if you need to kick someone away from yourself, kick them right here, approximately, and that's your best shot at accelerating the entire human at once. Sound good? All right. Now, related to center of mass is something else we need to talk about. The past couple torque examples we did are considered static in nature. The goal of the teeter-totter is, at least the goal that we had with the teeter-totter, was to keep it stationary, for the torques to be balanced and for the object not to start rotating. Same was true of this flagpole just now. We did not want it to rotate. Those are called statics, and again, that's what an architect spends all day doing. They want the building to be static so that it's not falling in on itself. For something to be static, the net force and the net torque need to be zero. But we've talked about motion, we've talked about acceleration. You know, net force isn't always zero, therefore objects do accelerate. It happens every time you fall. You have an acceleration because net force isn't zero. The same is true of torque. Net torque does not have to be zero, and that means that you can use net torque to cause angular acceleration. Again, linear force causes linear acceleration, so linear force pushes things in straight lines. Torque causes angular acceleration, namely it makes things start spinning. So if something begins spinning, that means all the torques on it don't add up to zero. The torques are imbalanced. The reason there's a plane on screen right now, whoops, is because all the torques on a plane don't equal zero if they start doing a barrel roll. The linear forces on the plane might equal zero if the plane stays at the same linear speed. However, a downward force on one wing combined with an upward force on the other, those are going to generate complementary torques that don't cancel out and cause the plane to start barrel rolling, or aileron rolling. So net torque does not equal zero all the time, and when it doesn't equal zero, you get angular acceleration, like similar to how linear force causes linear acceleration. The problem, I've shown you this formula a few times by now, and I've acknowledged the relationship between the torque and the acceleration is like the relationship between force and acceleration. Do you notice the part of the formula I haven't talked about yet? That big letter I in the middle. Yeah, that I is not the same thing as mass, unfortunately. Mass has an angular counterpart, and that's a fact that I hate. I don't like that mass has an angular counterpart. I'd rather mass just be used normally in the rotational equations, because mass isn't a vector. We shouldn't have to convert it. However, rotation is kind of weird in that matter sometimes doesn't want to rotate depending on how you're trying to rotate it. And for that reason, physicists invented the concept of moment of inertia. This is the I in that formula, which I realize I didn't actually write on these notes. So the I in that formula is called moment of inertia. So this is an I up here, by the way. I equals moment of inertia. That's what the I in those formulas has meant this whole week. And moment of inertia is considered to be the angular counterpart to mass. We've looked at how displacement, velocity, acceleration, and force all have angular counterparts. It turns out mass has one too. And what that means is mass has different tendencies to rotate depending on a few key factors. Matter may or may not want to rotate it depending on how you're trying to rotate it. It also depends on the shape of the object. You ever noticed how, you may have noticed that some shapes are easier to make spin than others. For example, humans figured out wheels pretty quickly in our development, thankfully. And wheels are very easy to spin, right? They're round, they're designed to do that. Shapes other than wheels don't spin as easily, right? There's a few reasons for that. One of them is different shapes have different tendencies of spinning, but even the same shape might spin differently depending on how you're trying to spin it. Here we have the wheel, and it spins very nicely like this, right? This is the entire reason we invented the thing, was to do this specifically. But that's not the only way I could spin it. If I wanted to, I could try to spin it like a top. Does this work nearly as well? Certainly not. You wouldn't want it to do this if it was attached to your bicycle. Furthermore, this is just harder. This is taking more force from my hand to do. And if you'd like to test this, you are welcome to come up and try. I encourage that, actually. Just compare the required force to do this to the required force to do this. This is way easier. Again, give it a shot. I encourage you to try it out. What this means is matter has different tendencies to rotate depending on, one, its shape, and two, the manner in which you are trying to rotate it. And I, moment of inertia, capital I, is a measurement of that tendency. Different shapes have different formulas for calculating their moments of inertia. This chart on screen right now is actually a pared down version of the chart on the back page of your formula sheet. So you have this table. You actually have a better version of this table in your formula sheet right now. Yours has more things on it, which is technically better. And all of these different shapes, we've got hollow cylinders, solid spheres, hollow spheres, and two different ways of spinning a metal bar. All these different shapes have different tendencies to rotate depending on their configuration of matter, which just means their literal shape, and also the axis you're trying to rotate them through. The formulas are all similar. They all tend to involve the object's mass times its radius or its length squared. I do understand that it might be a little blurry on screen right now. I do recommend you glance at the back page of your formula sheet if you'd like to see it a little better. Note again, all of those different I's, those different centers of mass, those different moments of inertia, slightly different formulas, but they all involve mass times radius squared or times length squared. But they all have a slightly different fraction attached at the front. There's no fraction here. There's a is that 2/3 or 2/5? Thank you. 2/5 here, 2/3 there, 1/2, 1/12, 1/3. You don't have to memorize any of those, by the way. They're on your formula sheet. If I tell you something is a solid cylinder, that means you can just look right here and you've got the formula for that particular object's moment of inertia. And what it means is just different shapes rotate easier than others. The lower its moment of inertia, the easier it is to make it spin. That actually means out of these solid shapes, they're just, well, mostly solid shapes that spin through their own middles, the sphere is the easiest one to make rotate, which again, is why tires are round. One reason why tires are round. Now, it can be weird to think that the same object might want to spin different ways depending on the axis, but in addition to the bike tire, which again, I do recommend you give a try, spinning in different ways and just noting the difference. There's another example of how one object spins differently depending on what axis you're rotating it through. And that's the case of what happens if you take an object shaped like this and throw it into the air. This is, we're just going to consider this to be a boxy rectangle. It's made out of nothing but carbon, so it's uniform enough for this purpose. You can try this with a book, you could try it with your cell phone. I wouldn't recommend it in case you drop it, but it's the right shape at least. I am going to throw this object in the air and rotate it through 3 different axes to prove, or try to demonstrate at least, that which axis it's spinning through affects its motion. First, I'm going to throw it into the air like this. I'm spinning it through its center of mass along this axis. I just want you to note how fast it spins when I do that. Consider that our baseline speed. It's pretty quick, in my opinion. Now I'm going to switch things up, and instead of spinning through this axis, I'm going to spin it through this axis. So I'm going to throw it like this instead. And I want you to note the speed difference. Rather the rotational speed difference. I'm going to do it the old way again real quick. Which way's faster? Yeah, the first way. It might not be super dramatic, but there is a difference. And again, if you've got your own book, you can give it a shot. But there's a third way that I can spin this too, and that's through this axis, because it's got 3 sides. But this is actually the really weird one. I want you to pay really close attention to this one. First of all, how does the speed here compare to the others? It's at least slower than the first one. It might be tied with the second one, but that's not the weird thing here. The weird thing is it does kind of a backflip. It kind of spins once or twice and then turns itself over through a different axis before falling back down. It can actually do it more than once if I throw it high enough. Ow. Do you guys see it? That's because this object uniquely does not want to spin through this axis. Its moment of inertia is so big that it just says no. And it physically turns itself to avoid having to spin that way. So the shape matters, and the axis you choose matters. And that's why we have these annoying charts. I personally hate moment of inertia. I hate having to do this. But it's just a part of physics, unfortunately. Now, what this means for you guys is, for example, if we do a rotation question involving the Wheel of Fortune, I'll tell you what shape you can consider the object to be. And the wheel is basically just a cylinder. It's a really thin cylinder, but it's technically a cylinder. And I will say within a question something to the effect of, you may consider the wheel to be a uniform cylinder for determining moment of inertia. That means if you need moment of inertia, if one of the formulas you use has I in it, you can turn back to this slide or the table on your formula sheet and note solid cylinder or disk, moment of inertia formula for that shape is 1/2 times mass times radius. So if I tell you what shape something is and it is spinning, you just check this table to figure out how to find its moment of inertia. You don't have to memorize any of them. I certainly don't have them memorized. memorize, you have this reference material. And I would never ask you to have to try to figure out on the fly the moment of inertia of a weird shape like a human or something. I will always tell you what very simple shape on here you can relate it to. Does that sound fair? All right, let's get a little bit of practice in. Let's look back at that Wheel of Fortune real quick. We're going to consider the wheel to be a very thin cylinder, just a disc. Its physical radius is, what did I say, 1.5 meters? 1.5 meters across. Its mass is 45 kilograms. And you, as a contestant, are going to spin it by exerting a force of 23 newtons tangent to its edge. Tangent means along the edge, but perpendicular to the radius, so that you generate torque. Again, if you want to make something spin, like with the bike tire, you exert a force perpendicular to its radius on its side, and that will generate torque trying to make it spin. Net torque equals moment of inertia times alpha. We want to figure out what that alpha is. We want to know the angular acceleration that's going to speed this wheel up from rest. And to do that, we first have to figure out how much torque did we generate, and second, what the wheel's moment of inertia is. Questions so far? All right. First up, there's only two formulas so far with torque in them. This is one of them, so let's just look back at the other. Torque equals radius times force. So we take that linear force we applied, multiply it by the radius of the wheel, then that'll tell us how much torque we exert on the thing. And if our goal is to find alpha, we need to figure out the wheel's moment of inertia to see how easily that torque can affect its motion. Since different shapes have slightly different formulas, we again check to see what type of shape we're dealing with. We're going to go with uniform solid cylinder. That means we should look again back at this image. See here, solid cylinder or disc, its moment of inertia is 1/2 times its mass times its radius squared. So that'll be what we put in here for I. And alpha is what we're looking for. That feel okay? Does it not feel okay? Better question. All right. And thankfully, we actually know all of these pieces of information except alpha, so we're set to solve for that. Wheel's radius is 1.5. We applied 23 newtons of force, so that's the torque we apply to the wheel. It's like at least 30 newton meters. That's going to be equal to 1/2 times the wheel's mass times the wheel's radius squared times alpha. Does anyone's math disagree with an alpha of 0.68 radians per second squared? All right. So that means as long as you are applying that amount of force for about a second, you'd spin the wheel up from 0 to 0.68 radians per second after applying that force for 1 second, which is pretty slow, but the wheel doesn't spin all that fast on TV. Questions, concerns? All right. Now I will say, moment of inertia is tied for one of my least favorite parts of physics. I hate having to deal with it. I'd rather mass just be mass in these formulas. I think it's kind of silly that we need to find I. I kind of hate that mass rotates differently depending on shape and axis. I'd rather just put n in the formula because mass isn't even a vector. Why do we need to convert it? I hate this, but tragically it's part of the content. It's tied for my least favorite thing up there with questions that take too much algebra. But we're going to continue practicing it on Friday. Friday, my plan is to cover the last couple concepts in chapter 8, namely looking at a few more of these angular concepts, a few of which do have i's in them if their linear counterparts have m's in them. So that's all Friday is. More moment of inertia practice to familiarize ourselves with it and just seeing how it factors into angular momentum and angular kinetic energy. Any questions for right now? All right. In that case, let me know if you need anything. Make sure to bring these notes to your lab if you haven't had it yet, and have a great day.